Every groundbreaking discovery starts because someone dared to ask, why? How? What if? From bold ideas to global change, what turns a question into a breakthrough? Chemistry is the answer. It colors our world, advances technology, improves health, strengthens education, and brings sustainable ideas to life. It's not distant or abstract, it's us. Chemistry is human. At the American Chemical Society, we know chemistry is more than science. It's what shapes our world. Guided by integrity, fueled by discovery, and open to all. Chemistry is everything. Since our founding, we've supported researchers, educators, and innovators, a global and inclusive community united by a passion for chemistry and committed to learning, advancing, and improving lives. 2026 marks our 150th anniversary, a year to honor our history, celebrate our community, and imagine the future we can create together. Let's celebrate all year long and welcome the next era of chemistry. Because when we move together with science, with purpose, everything is possible.
Please join me in welcoming to the stage 2026 ACS President Rigoberto Hernandez.
ACS 150 chemistry is everything. To the smart, guessing everything from the smallest atom.
Are you chemists in the room? Yeah. This is a day to celebrate chemistry, like every day, because chemistry is everywhere. Good evening, everyone, and welcome to the ACS 150 Keynote Address. It is an honor to gather together for this truly special moment as we celebrate the 150th anniversary of the American Chemical Society, a milestone year that reflects not only the extraordinary legacy of the ACS, but also the enduring power of chemistry to shape our world. I want to extend my heartfelt thanks to each of you for being part of this celebration. Whether you're here in the room or joining us from across the globe, after all, chemistry is everywhere. That's why that's my social media handle. More than that, chemistry is everything in every discovery, every innovation, and in every one of you. You exemplify what it means to carry this science forward. Throughout this meeting, we have seen the energy, brilliance, and curiosity that continue to spark new ideas and ignite progress. And today's keynote is designed to capture that spirit, to bring our celebration to a high point as we close this gathering with momentum that will carry through the entire anniversary year. While today marks our ACS 150th keynote celebration, it is certainly not the end of the festivities. In fact, we invite you to continue celebrating with us on ACS Founding Day, April 6th at 10 a.m. Eastern Time during a free virtual community event open to all. We hope you'll join us and help extend this milestone celebration across the ACS community and beyond. Now, of course, we're not just here to talk about the history or the future of ACS, but to hear some truly groundbreaking science. But first, a quick story. Last fall, I taught a class on human intelligence, computer intelligence, and artificial intelligence. In that class, I challenged my students to predict who would be the 2025 Nobel Prize winner. At the time, I used AI to see who were the maybe 12 to 15 most likely teams. Dr. Omar Yaghi was not among them. I discovered that the reason was that ChatGPT had instead listed Omar Yaghi as the winner of the 2024 Nobel Prize. With no disrespect to the very deserving winners that year, David Baker, Demis Hassabis, and John Jumper, what that suggested to me was that ChatGPT, that outdated ChatGPT, felt that Yaghi was already ready for the prize. Nevertheless, I had my students pitch for their top 12 of these groups, which of course now included Yaghi and Kitagawa, and at the end they voted. Because of course they know I'm a theoretical and computational chemist, they decided to go with Roberto Carr and Michele Parinello. But I went on record as predicting that Yaghi and Kitagawa would win. Now this is not about me or my prediction, but I will take money on the side if you want. But rather, the point that it was only a matter of time, even if it was a year later than AI thought, that today's speaker would receive the Nobel Prize. And it is my pleasure to introduce him to you today. Professor Omar Yaghi is internationally recognized as the pioneer of reticular chemistry. The field focuses on connecting small molecular pieces into sturdy, repeating structures. His groundbreaking development of metal-organic frameworks, known as MOFs, earned him the 2025 Nobel Prize in Chemistry, recognizing materials that can capture gases, pull water from dry air, and help address global challenges. In addition to MOFs, Dr. Yaghi expanded the landscape of new materials by co-creating covalent organic frameworks, known as COFs, and zeolytic imidazolate frameworks, known as ZIFs, innovations that open the door to thousands of new structures that are now shaping the future of clean energy and sustainability. Thank you for being here. Thank you for all you contribute. And please join me in welcoming 2025 Nobel Laureate Professor Omar Yaghi to the stage.
From atoms small to the lives we shaping, every bond, every reaction.
Thank you very much, Roberto. Thank you for that dynamic introduction. It's really a great pleasure and an honor to be giving this lecture for the 150th celebration of the ACS. And thank you, Roberto, for continuing the tradition of this great institution that never loses sight of the future, but also focuses on the present to enrich our lives and the lives of all chemists worldwide. So thank you very much. I am especially touched today to see so many young scholars amongst you who have stayed to the end to hear what I have to say about organic chemistry and AI for our planet. So today, this topic, I will start with the following. The Nobel Prize was awarded for the development of metal organic frameworks. And they're based on coordination chemistry. And Alfred Werner discovered and determined the structures of the very first coordination complexes. And it was really an incredible start for inorganic chemistry that extended to the current metal organic frameworks. We use the same principles outlined in coordination, the original coordination chemistry, to build a whole new class of materials. And more than that, to develop a process by which one can control matter on the atomic and molecular level. But there's one thing that was done that basically said to all of us that we are entering a new lineage of inorganic chemistry. And what is that? It's going from molecular chemistry into the infinite extended regime, so that we can encompass space within which matter can be further controlled and manipulated. And that's what chemistry is about. It's about how to control atoms and molecules and how to control their reactions. So here's a lineage of organic chemistry. That's the beginning of my talk. And you can see all of good students of organic chemistry are familiar with this lineage. All of it has led to tremendous improvement in our lives, in the lives of everyone around the world, not the least of which the discovery and the synthesis of pharmaceuticals and polymers and other such contributions. Again, organic chemistry lineage is entirely based on discrete molecules. And today, I want to show you that there is another linkage, another lineage. It has linkages. This lineage is that of covalent organic frameworks, which are yet another class of materials not recognized by the Nobel Prize. Well, not yet. And the story starts here with a great chemist and his paper in 1916, The Atom and the Molecule. Every student of chemistry should read this paper, because in this paper, he outlined how atoms can be linked together to make molecules, and he struggled a lot with trying to figure out the geometries of these molecules. And in the end, he got that mostly correctly. But these principles that he outlined in this paper on how atoms can come together to make molecules became what we call today the covalent bond. And in my lecture today, I want to show you this lineage, the lineage of the atom, the molecule, and the metal organic, or excuse me, the covalent organic framework. Here it is. You can see in dedication to Lewis, I have the Lewis dot structure for the atoms. They make the molecules, and then they make the framework. Now, the molecule to the atom is what the COF is to the molecule. Let me explain what I mean by that. Is that the molecule puts the atom in a very specific connectivity and geometry and spatial arrangement. Again, the control on the atomic level, while the covalent organic frameworks, or the COF, puts the molecule in a specific geometry, linkage, and spatial orientation. But something that the molecule doesn't have, that the COF has, that is that the COF encompasses space within which one can trap matter or carry out reactions that you can't do any other way. And so here is the space indicated in yellow. Now, in my lecture today, there are two things I'd like you to focus on. The linkage. The linkage is where all the chemistry takes place when you're assembling the COF, because you're taking well-defined molecules and you're linking them together, you're making new bonds, and you take the linkers, and you can see the linkers do not undergo any change. And what you're forming are just the linkage. In this case, it's a B3O3 ring. In other cases, it'll be one bond. So when you think about it, COFs are the very first class of materials to be made by design. Why? Because the molecules do not undergo change. They just are glued together through these linkages. Okay? But everything has a start, and sometimes the starts are very challenging. So my very first students who I got coerced or got them interested, let's say, into making COFs, when they assemble molecules with strong bonds, this is the X-ray powder diffraction that they obtained. Okay, that tells you there's hardly any diffraction. This is very bad. And for most students, they run away. Okay, they go on and they develop other things that work, because smart students want to do reactions that work so that they can publish a paper, so that they can go on and get a job, so they can develop their lives. And this is not a way to develop your life. This is very discouraging. Okay, so instead of graduate students, we ask the undergrads to take a risk, as you will see shortly. But the undergrad understood that I have to overcome the crystallization problem. What is the crystallization problem? The crystallization problem is that to make a crystal, I need to be able to combine these building units in a reversible fashion. They need to come together and they need to separate and come together again at a better orientation to make a crystal. That's called microscopic reversibility. That's thermodynamics. Then the next thing is kinetics. You need to have this process of assembly to be not too slow, because if it's too slow, you don't make large enough fragments to call crystal. If it's too fast, then you make that horrible hump, the amorphous stuff. Okay, so what do chemists do to overcome problems? We find the recipe that would allow us to crystallize. That's what chemists are so good at. We use trial and error, we use our chemical intuition, we use all kinds of talent that we might have, a knowledge, to find that recipe. In organic chemistry, those recipes are named reactions. We didn't name these, but we should have named it after this undergrad. The undergrad is Annabelle Benin. She looked at the top reaction and she said, whoa, this reaction is a nice reaction to do because it's basically a dehydration reaction. It's a simple reaction. Okay? And if I put a diboronate, as you see there on the bottom, I should be able to make a covalent organic framework. That's easier said than done. Now, that building unit, the diboronic acid, is going to assemble into that structure and only that structure. There's no other way for it because it is directional, it is rigid building unit, so there is no other possibility, especially since that unit up there that you see with the triboroxine ring is actually planar. The fact that it's planar means that you're going to make this kind of structure, what is labeled as COF1. So she tries all kinds of things, and one day she comes into my office and she says, Professor, I turned that big hump, it's still there actually, but I found a very tiny sharp peak in the X-ray powder diffraction. And it's at high D-spacing, and that meant that potentially she made something larger than the molecules that originated in her reaction, that she used in the original reaction. And I said, okay, that sounds interesting. Go back and make it more crystalline, get more sharper peaks. She went back, and after 2 weeks, she came back to me and said, I noticed that the intensity of that peak varies depending on how tall the tube that I run the reaction in. We ran the reactions in sealed tubes. And depending on the length of the tube, she could get more or less crystalline material. So there was a control. That is, very quickly we realized, hey, water is a byproduct, and water is hovering above the liquid and it's pressurizing the reaction, and therefore I can use that to have this microscopic reversibility. Once we knew that, and that's what's great about chemistry, once you know the secret for what makes the reaction goes, then it didn't take us very long to make that hump into very sharp X-ray powder diffraction peaks. The moral of this story is that an undergrad opened the door to the development of a whole field of chemistry called covalent organic frameworks. And a postdoc came in and cleaned up the data that she left, of course, to do other things, and that's what you see here. The structure is exactly what we predicted, except the stacking, not easy to predict. The actual framework you can, but the stacking of these layers is not so easy to predict. In this case, it's a slipped graphitic layer. Well, once you know the recipe to make one COF, then you use that recipe or a variation, slight variation thereof, to make three-dimensional structures. And to make three-dimensional structure, you use a tetrahedral tetraboronate to make an extended structure as you see here. And I won't bore you with the networks, but these are the two possible structures. Needless to say, we made both. Here's one of them. And notice that the recipe is not different than the original one. Just slightly longer time, you make that crystal. Okay? So in one shot, as you can see, the X-ray powder diffraction, the calculated, the one we anticipate, and the one that we actually make in the lab. That's the power of this chemistry. If you think it, you can go to the lab and make it, and now, having the right recipe in place, you can make it as a crystalline material. Why do we want crystals? Because chemists need to know what they made. And crystallography is the most definitive kind of characterization. We can characterize materials on the atomic and molecular level. So, in just those few slides, we've covered 2D extended structures and 3D extended structures. And we've extended chemistry beyond the molecule. And I would say it's a new lineage in chemistry. This area is developing in parallel with molecular chemistry. And it's offering things that molecular chemistry does not offer. So, the hump is now called POPs, porous organic polymers. And these are just the failures that we have on the way to making a crystalline COF. And POPs, I would say, are not crystalline. It's okay if you work on POPs. No, they're not my favorite, because I like crystals. And COFs are crystalline. And please, 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 you should not call COFs crystalline polymers or organic polymers, because, in fact, they are extended covalent solids. We don't call diamond a polymer, do we? It's an extended structure. So that's where we are in terms of the opening of the field of COF. Using the same strategy of balancing the thermodynamics and the kinetics by varying the conditions, now the students got rid of mesitylene and using acetic acid to make the imine linkages. Well, imine linkages are sensitive to acid. They use that to reverse to have this microscopic reversibility and ultimately make crystals of the imine reactions. And even longer linkers could be applied to make larger pore structures. In this particular case, the structure you make is a diamond network, and it likes to self-catenate, meaning to fill its pores with other frameworks. And we collaborated with Xiaodong Zhu, who is very good at doing rotation electron diffraction, red technique to figure out the crystal structure using electron diffraction of this COF. And it turns out that it has 9-fold interpenetration. 9 frameworks are entangled within each other to fill each other's space. So what other linkages could we do? We've done, I showed you boronate ester, and boroxine, boronate esters, triazines, imines, hydrazones, borazines, phenazines, linkages that organic chemists for a long time thought are not reversible. Now we believe that anything is reversible provided you find the right conditions, imides and so on and so forth. Oxazoles, thiazoles, you can see that. A dream come true. If you can think it, you can make it. And you can make it from linkages that are the favorites of organic chemists. And not only that, now you can see where I'm going with this. Now I am making COFs from the strongest bonds known in chemistry. And therefore, these COFs are extremely stable in solution, thermally stable, and they have both thermal stability and chemical stability. Now, the results I showed you, the structural results, are all based on powder diffraction, X-ray diffraction, which is fine. But powder diffraction doesn't give you atomic resolution. So we pushed ourselves, and a key person in all of this is Tianchun Ma. She's actually here in the audience. And what she did is she put a competitor here, which is this aniline. The aniline competes with the diamine and acts as a modulator to control the imine exchange and therefore control the nucleation and make single crystals of extended organic structures. Okay, these crystals that you see here, depending on the amount of aniline that you add, you can vary their size. And this size is amenable to X-ray diffraction. What am I saying here? I am saying we can design COFs with the precision of molecular chemistry, molecular organic chemistry, and we can characterize them with the precision of molecular chemistry. That's why this is an amazing new field. It goes on. This is something I've never dreamt could be crystallized, could be made as single crystals. Recently, this great postdoc has done that. Okay, so let's talk about what these things do. How will they serve society? A CEO of a major chemical company very early in my career, when we were making MOFs and COFs and I came to visit me, he asked me, what are they good for? And I was taken back by that. I said, I'm a scholar. Scholars push the frontiers of knowledge. We do not worry about applications. Let society do whatever they might with it. Okay, and he said, well, you can be an excellent professor doing what you're doing, but you can never be a great professor if your inventions don't reach society. And so that was really, I was taken back by that. So mentors can come in all forms, by the way, at any time of your life. And he was a great mentor. And he pushed me into taking these materials into applications. I want to show you how organic chemists can now capture carbon dioxide from air, one of the most difficult problems facing the planet. So here's a structure made from olefinic linkage. And Haolu made the structure in crystalline form. You can see the conditions under which he used to crystallize this material, and you can see it has very nice sharp diffraction peaks, and it's very stable even in concentrated acid, concentrated base, boiling water, anything you want. That's the kind of stability you need so that your material, which is a powder in this case, can stay in a power plant for years, capturing CO2 from a power plant before it reaches the atmosphere, or taking CO2 out of the air, which we need to take anyway. Even if we stop burning fossil fuels, you need this stability so that you are not replenishing the material every other cycle. You need to cycle for years, and the material need to withstand all that cycling. You're trying to push the entire atmosphere, the entire air in our planet's atmosphere into this material. So it has to have this extraordinary stability, which is provided by these carbon-carbon bonds. So another student came in, Zihui, and he did a marvelous thing. He made the skeleton of this material based on the chemistry that Hao did, and installed amine units covalently within the pores. Okay? Because in the separation of CO2 from air, which is the thing I want to discuss here, it's a difficult separation. For each molecule of CO2 in the air, there are 2,500 other molecules. So it's a very, very difficult separation. And in order to affect this separation, we use these amines. We bind them covalently into the framework so that they don't escape during the uptake and release of CO2. And their amines are the sites onto which CO2 will bind. Okay, so this is what the powder looks like of this COF. We call it COF 999. And after we had the laboratory results, I said, well, prove it to the world that you can take Berkeley air and separate CO2 from Berkeley air, open air. So he did. Okay, on top you see the amount of CO2 that is in Berkeley air, around 450 ppm. And then below that, in the black line, you see the level of humidity in the air, which is around 40% or so relative humidity. And below that, you see in the bar diagram how much CO2 is being taken up by the material. And you also notice that the variation in the uptake has to do with how much humidity is in the air. The more humidity, the more CO2 is being taken up by the material. So the material loves to have a little bit of water into the pores, and it helps push the equilibrium of CO2 binding towards more CO2 bound species. Now the magic about this material is that it releases the CO2. When it's fully loaded, you can release the CO2 at very mild conditions like 50 degrees Celsius. Which means that when I have this in a plant, I could use waste heat to remove the CO2. So the whole thing can work on waste heat rather than adding new heat that I have to pay for. This makes the whole process of binding CO2 from air far more economical than what you're using now with the liquid amine solutions, which are toxic and they decompose, and they're liquids, they have high heat capacity, and so they require a lot of energy to operate. So these numbers operate not just for air, but you could use these materials not just for air binding, but also for power plants that use coal, burning coal or burning natural gas. So this work has been done by Zihui and my great collaborators on computation, Laura Gagliardi, she's up front here, and Joachim Sauer. It was very important to have a team of computational chemists and experimentalists working together to try to understand what makes for a great carbon capture material. There's nothing like this out there. This is the very best material for capturing CO2 from air. That undergraduate opened the door to making a whole new class of materials, and then these whole new class of materials are being used to address one of society's biggest problems. That's the beauty of chemistry. One little discovery propels you to the sky. Okay? That's the beauty of chemistry. So what does CO2 capture from air look like at scale? Okay, there's a lot of numbers on this, and they're big numbers, so please prepare yourself. There's about 1,100 gigatons of extra CO2 that's in the air. That's above and beyond the natural amount. We put that in the air as a result of burning fossil fuels. Okay, if I use the material that I just described to you, the COF, it works at around, right now we have improved it to have about 2 millimole of CO2 per gram. That's its capacity. Each cycle takes up 2 millimole of CO2 per gram. And each cycle is about 10 minutes, meaning taking in the CO2, and then when the material is filled with CO2, you take it out, you compress the CO2, and you pump it under the ground. Ideally, you want to take it and convert it to something useful. But that's still a challenge, and it's still something that we are researching. But let's say, based on these parameters, let's gauge what we need. If I have a plant that has 100,000 tons of COF, I would capture half a gigaton of CO2 every year. That would take me 2,000 years to take the CO2 out of the air. Okay, that's not very practical. But if I look at just the cities around the world that have 1 million people or more, and I put one of these plants in those cities, that's about 700 or so cities, I can do the job in 3 years. And before you tell me this is highly impractical because the scale is just too much, well, the chemical industry is amazing. They produce 200 million tons of sulfuric acid every year. And that's a liquid. We are making solids. Okay? Should be a lot easier to do. And this is the issue we need to think about, is that DOE, as an initial requirement, requires us about $100 cost per ton of CO2 we bind. So that means we need $100 trillion to do the job. That's as large as the world GDP. Look, it's a big problem. It's a crisis. And it has accumulated over the last almost 100 years. So you can't address the problem overnight, but you can be smart about it. And look, I could use 4% of the world GDP to dedicate it to addressing this problem. We do that all the time. When we had the pandemic, we dedicated in the US alone about $1 billion just to address the pandemic problem just in the US. So if we think about this as a crisis, we can solve the problem. So 4% gets you 25 years. Okay, I think the driving force for this is not just the will of the people and voting for the right people to put in office that consider this a crisis, but the fact that it's already costing us trillions of dollars to address problems of climate change, weather patterns, hurricanes, whatever, severe hurricanes. That's costing us a lot of money already. That's going to drive us to solve this crisis. Okay, that's one of the drivers I think that's going to. But this talk is about chemistry, okay? And chemistry, imagine if Zihui could double the uptake, or he could do a cycle instead of 10 minutes in 5 minutes, maybe 3 minutes. Do I have that slide? No, I don't have that slide. I just want to tell you that he just published a paper in Nature Sustainability telling the world that each cycle could be reduced to 3 minutes from 10 minutes. That means that 25 years I just showed you gets cut back by that much. Okay? So that's the power of chemistry. And that's why I am very optimistic about this problem being solved. There's another problem that COFs can solve, and that's the water problem. I know I've talked a lot about MOFs for water harvesting, but we can also use COF. Now, this chart shows that in fact a quarter of our planet by the year 2040 would be experiencing a water crisis, not just a water stress, but a water crisis. They do not have enough water to satisfy their needs. And many places, as you can see here, London, Brussels, are going to be water stressed because we are using more of our underground water than is being replenished. So we have a water crisis in the world. Okay, here's a COF. Here's an imine COF made from these two building units. And look at the X-ray powder diffraction, very different than the one I showed you at the beginning. Very, very sharp. We can make them highly crystalline. They need to be highly crystalline to function in an efficient way for water harvesting. And here's the water harvesting. This sharp step that you see tells you that you have a material, in this case, that operates at around relative humidity of about 25% to 30%. That's almost the average relative humidity in most arid regions of the world. With MOFs, we can even take the water out at 10% relative humidity. But here you see this amazing behavior and this repeatable behavior where the material does not degrade with water uptake and release. Why? Because we build the material from strong bonds. So this is a very active area of research. Let me just say that with MOFs, we already are producing units, I won't show it here, but units for water harvesting that will be deployed within 2026. And here, MOFs would be the next generation materials. Okay, so now I want to talk in the next few minutes about ametry. Ametry is a new field of science focusing on chemistry, materials, and AI, blending AI with materials and chemistry, and it's about something we all would love to do, which is AI for the design and synthesis of materials, and for connecting chemical structures to properties, and more importantly, the reverse, connecting properties with chemical structures. And reticular chemistry is ideal for application of this field. So let me just show you one example of how powerful these LLMs could be in helping us in our chemistry. Here's a COF. I won't tell you why we're interested in it, but we're interested in it because it's a very difficult COF to crystallize. And within the last 10 years, several groups have been trying to crystallize this COF. Many groups try to crystallize this COF, and the X-ray powder diffraction is shown there. It's crystalline, but not so crystalline. For water harvesting, you need materials that are highly crystalline so that all the adsorptive sites of water are homogeneously distributed throughout the material, so that when you take them out, you only need a small switch of temperature to take those water molecules out. So it's very important to figure out how to crystallize this. It's easy to make COFs. It's much harder to make them as crystalline materials. So students would spend years in trial and error trying to make them crystalline. And we need that crystallinity. I'm obsessed with crystallinity because I'm a chemist, because we can identify the material on the atomic and molecular level. Okay, so what does the researcher in my group does? They write a page and a half of prompts, and you can read them. The prompt: you are a reticular chemist developing a beta-ketoenamine COF. A robotic platform will execute the experiment, and all post-synthetic steps are standardized, blah, blah, blah. You can read all through this. This is exactly what my students would do without ChatGPT, but now they're putting it in ChatGPT, and here's more. Find, select precursors, select the appropriate temperature, select solvent and catalyst and blah, 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 composition. Even, look at the bottom, check for accuracy and reproducibility, and create a list of references. So that's all what a researcher does. And then a robotic platform, okay, then it gives you different conditions under which you should be able to crystallize that COF. Most of these conditions are things that I and my students would have guessed, but some of them aren't. And very tiny few of them are things that we would have never thought about because we didn't make connections between what's going on in the literature. And so it does all of that very nicely. Okay, so we take these conditions and we put them through the cycle. ChatGPT gives you the conditions. We solid dispense this in a robot, and then we put the reactions. The reactions are being carried out in wells, and we incubate them. We do whatever is needed to cause the reaction, heating it up in an oven, you wash them, and you do high throughput PXRD, and you feed the results of this crystallinity back into ChatGPT. And you keep doing this cycle, okay? And you do it once, twice. In this case, we did it only 3 times, okay? And the result is that we tripled the crystallinity of that COF. So what would have taken, well, it has taken 10 years without success of the community, now we can do in just a couple of weeks. That's transforming everything that I do in my lab. Okay, is that the use of LLMs is simplifying the tasks, it's making things faster, it's making researchers consider facts rather than chemical intuition when they're deciding their experimental conditions. That's very important because chemical intuition may not always be correct. In fact, most of the time it's wrong, because it's based on my belief. When I give my students my biases about what conditions to try, and the senior graduate student gives the other students the biases that they've learned over the last 4 years, it doesn't work. That's why it takes 3 years. But ChatGPT puts all these facts throughout this potential space before you, and it makes those decisions as to what conditions will lead to crystalline material. This is a beginning of a revolution. And it's not just LLMs, but also its diffusion models, its machine learning algorithms that have been adapted for specific chemistries. In this case, you see 3 loops. The blue loop gives you an AI predictive cycle, where you're predicting what structures would be interesting. The second loop, the yellow loop or the orange loop, is the experimental loop. So you do the prediction and the experiments side by side so that they are mutually informing each other. And then I would add a third cycle, because we're interested in taking molecules to society. The third green cycle is the scale-up cycle or the scaling cycle. There's no use, as that CEO told me, no use of just making a material and studying its properties. You've got to take it to address societal. So these 3 loops work together synergistically. And I just want to give you an example of the result. We just published this, actually, this paper. The results of just using the first 2 loops is that the students that use the first two loops in the area of ZIFs in my lab, we haven't applied this to COFs yet, double their rate of discovery compared to students that don't use these two loops. Okay, that means I have double the chance of discovering the next great CO2 capture material or whatever, water harvesting material, whatever property I am interested in. So this is the future, and my statement to especially the young scholars amongst you is that you don't need to wait for the professor to tell you to move in with AI and LLMs. You can do it on your own and drag the professor along with you, as my students have done. Okay, in my final segment, I want to talk about weaving, because weaving is the outcome of COF. It's one of the greatest applications of COF. It's the oldest way of making anything, right? And we still use the same kind of weaving today, except we're more sophisticated and we do it faster in different patterns. So here's a movie.
Ready for weaving. This is a loom, a weaving machine where warp and weft threads are interlaced to make fabric. Here are the warp threads slowly being drawn through the loom. Parts of the loom go up and down and backwards and forwards. Up and down. Heddles in action separating the warp threads. Backwards and forwards. The reed in action closing up the weft threads. And now the shuttle containing the weft in the pern. Here's a new pern being placed in the shuttle. It's a busy machine and often a noisy one. The shuttle flying backwards and forwards, interlacing warp and weft, using thread to make fabric. Perhaps if we have a diagram, we'll understand a little more clearly what's going on. That makes it a little easier. But let us go right back to the beginning. That's better still. Now we know where we are. Here's the warp threads that run the length of the cloth. And here's the weft, threads that run across the cloth. But the point is, how does the weft go over and under the warp? It's the heddles that will show how this is done. We'll bring them back. And we'll see what job they do. Up and down, separating the threads. Now for the shuttle which flies across. It's followed by the reed which puts the weft in its place. The fabric moves on. Now we'll watch all those parts at work and notice especially how the moving heddles cause the weft to interlace the warp.
Okay, try to do this in chemistry, right? It's very complex. So for many years, I would ask my students to look at patterns like this and say, could we make this? How could we make this? And try to inspire them to think of different ways of doing this. And of course, they all ignored me because it was a madman request, right? How do you take all these threads and interlace them in a periodic fashion? This is not chemistry. There's something here that you have to do on the molecular level. But a reticular chemist, as soon as we realized that all I have to do is make the intersection as a molecule, now I can control the angle between these intersections, between those molecules, and make a woven structure without actually having to interlace those threads. That's the new thinking that reticular chemists think about, and that is, what is the building block of a pattern, and how can I identify a molecule that would get me that building block? So the building block of this pattern is the crossing. And the crossing has already been made by Jean-Pierre Sauvage in making his catenanes. Okay, where you have a copper, you bring in two phenanthralenes, and now you use COF chemistry to functionalize it with amine and with aldehyde to make imine linkages, and there it is. That's how you make the fiber. The metal, the copper 1, brings these threads together at periodic intervals, and you make a crystalline material. And Yuzhang very quickly was able to make this once we realized that you need the intersections. So you can take the metal out to make the non-metallated form by just adding potassium cyanide, or you can reverse it if you want. And it doesn't get untangled, it's still interlaced, it's still woven, okay, because you can see here in the X-ray powder diffraction, the original material, the metallated one, COF 505, and then when it's demetalated, it becomes a fabric, very flexible and therefore not so crystalline. And then you metallate it and it becomes crystalline again. So that means it has not been unzipped. Okay, this is how crystalline this material is. Okay, so it's almost anything you can imagine, any network you can think of could be woven. All you have to, because weaving requires intersections, and molecules can provide you with that, and if you can control the angles between those molecules, you can do all of this. You can have threads that are interlaced or polyhedra that are catenated together, as you see here. So here's one that was made by Tian Chun. It's made from these adamantinoidal units that are interlocked within each other to make a 3D chainmail. Chemistry is wonderful. You find the intersections, you functionalize them accordingly to do COF chemistry, and there it is. Okay, that's a crystal structure. It's a diffraction structure from electron diffraction, and this is what the structure looked like. Each adamantane is surrounded by 6 other adamantane to make each granule has millions of these adamantanes that are catenated to other adamantanes. Okay, so here's another example. Chicken wire, what does it require? It requires a helix linked to other helices. Well, Jean-Marie Lane already reported this, 30 years ago, these building blocks, these helicates, okay? And we can link them together to make, and these are crystalline, this is their crystal structures. This is what reticular chemistry is about. It's about building structures from molecular building blocks. And you look at it now and say, wow, that is really complicated, but from building blocks, it's not. And we've already developed the COF chemistry for it. What about 1D?
Steel cutters now make notches on both sides of the wire. These notches mark the place where the wire is to be sliced into link-sized pieces. A mechanized knife makes the final cut at the notches. Next, roller arms loop a cut piece of wire around a steel finger. The roller arms make it look easy, but they're actually exerting tons of pressure in order to shape this wire. After the rollers form the link, a pliers link tool grabs it and turns it around. This positions the completed link so that it can connect with the next link as it's shaped.
Okay. I'm happy to report that we can do that. And why? Because chemistry is unbelievable. It's an amazing field. Here it is. Here it is, and it's made from those building units. Again, intersections. In this case, tetrahedral intersections linked by these bent linkers. We add additional bent linkers to take away the metal before it gets incorporated into the structure. So you make a nice chain. Why is this all very important? Why is the weaving so important? Molecular weaving is so important because when you blend it with polymers, with structural materials, it transforms their properties. So usually when you add additives to materials, you make them stronger but more brittle. That has been sort of the biggest problem with additives in polymers. Okay, now with these additives, not only are you making them harder, but you're also making them more flexible without being brittle. Why? Because your catenation absorbs the energy of stress without having to stress covalent bonds, you're just moving this catenation rings with respect to each other, or the threads with respect to each other. So here's my last view here is that, excuse me, you have, let me try that again. We're pulling onto this piece of polymer, and the first one doesn't have molecular weaving, okay? The second one has 1% by weight addition of molecular weaving. And you see it takes much longer to break that. And the next one after that is 3% and 5%. Just by adding a tiny amount, it gets distributed throughout the material, and it completely transforms its mechanical properties. That's really a beautiful applications of molecular weaving. Okay, so this is the new lineage that I'm talking about for organic chemistry. It starts with Lewis, it goes on to make host gas complexes, and now we are in the extended regime. Okay, I want to acknowledge the students that I've had over the years because they were brave enough to fail and fail and fail so that they can succeed. They have always inspired me because of that. And my former visiting senior scholars, former visiting students, and many of them came to Stockholm, and they couldn't go to the actual ceremony, but they can watch it on TV, and then the next day we can have a nice brunch together. It was one of the most moving times of my life. I saw my life in front of me, from the early students all the way to the current students. I want to acknowledge all the funding that I've had over the years and the loyal funders who believed in our research, and UC Berkeley, and I want to thank you for your attention. It's been an honor.
Welcoming back to the stage, 2026 ACS President Rigoberto Hernandez.
Wow, such amazing chemistry. So many structures, so many possibilities. We have time, and with my regrets, for only 4 questions. So the first couple that get to the slides, we're going to get to those. And wow. Okay, that's 3. You got it. You got number 4. You go right over there. So I'm going to take you 4 in turn, and because the 3 of you were there, I'll take 1, 2, 3, and 4. Professor Yaghi, are you ready?
I am ready.
All right. Question number 1.
Well, thank you for the really amazing speech, and it's such a great keynote to sort of like, kind of like wrap up this sort of convention. But like, I find it great sort of a little bit of irony that like this use of LLMs has basically fueled this sort of new revolution in this sort of field to try to combat the problems of like water problems and climate change, when at the same time these sort of like AI has been kind of in the conversation for basically sort of inducing this, like we talked about data centers using up a lot of electricity and using a lot of water and using a lot of power that, because we're still using fossil fuels right now, kind of sort of contributes to this sort of problem. And so I guess my question is, how do we establish a balance between those, I guess, those 2 sides, right? And I guess one thing you could say is, how do you establish a sort of framework between the public and chemists and government to basically, I guess, maximize the good parts while minimizing the not so good parts?
Well, I think most researchers, when they do their research, and especially like our research that is close to applications to society, we always are thinking about how can we make the materials cheaper, more sustainable? Could we develop chemistry that these materials can last for years so that we don't have to keep using resources to make those materials? So I think we need to be more conscious of that, but I am not a fan of conservative thinking. Is that the value of progress in society sometimes comes at this kind of cost that you're talking about, but that's for a conscious inventors or conscious organizations. They build in, or should build in, thinking about how these things could be sustainable. And the fact that AI and AI data centers are energy intensive right now may not be true in 2 years or 3 years. So we need to keep pushing the frontiers of science, because the benefit to the way we think and to solving problem is much, much larger than the negative problems that might emerge. And if we are really responsible, we should think about ramification of our technologies.
Thank you. We're going to take the second from here, and then the third, and then the fourth. So second, please.
Thank you. Thank you for the inspiring talk. Besides applications in tackling challenges in climate, water, imagery, and weaving, do you envision materials like MOFs and COFs expanding benefits to public health, particularly around the environments where people live, work, and spend most of their lives?
Yes, yes. So there's a lot of research covering both biomedical applications, like, for example, cancer therapeutics, but also research into cleaning air in household environment and things like this. A lot of research. Almost every sector of society, of industry, can make use of MOFs and COFs. Not just clean energy, clean water, clean air, but also biomedical applications and other applications. Yeah, it's a very large field.
We can go to the third question, and then we'll go to him at the end. I sequenced by who went to the bank first. Yes, please.
First of all, thank you so much. The presentation was extraordinary. My question, a lot less technical, would be, what advice would you give for younger scientists, this new generation of scientists and engineers, to kind of take up space and to kind of drive meaningful impact?
Well, there's never been a better time to do chemistry and science than now. The tools available, the facilities, the resources are immense. So I think that that's important. But how do you take advantage of this? Do the experiment. Instead of theorizing about why the experiment shouldn't be done, it's a lot easier to just do the experiment. When you do an experiment, you open the door to discovery, and that discovery may change the world. So that's my advice.
Thank you.
Yep.
Last question.
Okay, it might be two, but I'll stick with one. And so when you do the weaving, what exactly are the synthetic mechanisms? So what happened was, how do you, that when you have you have highly repulsive intermolecular forces, whether they've come from the Pauli exclusion principle or electrostatics, how do you overcome these intermolecular forces so that you can do the weaving? That really impressed me.
Yeah, good question. This guy always asks hard questions. Okay, he got me in my last talk too. Okay, good question. Thank you. Very good question. Now, in reticular chemistry is all about putting your linking units as far away from each other as possible, so that you can, through the interactions of these units with other units, which is a dominant, let's say, interaction, they can dominate rather than the potential pi-pi interactions or the weaker interaction that may result. I'm not saying that in our reaction we don't get few percentages of what you're talking about, a non-woven or molecular structures or extended structures that are interacting, where the building units are interacting by weak forces. But the fact that your intersections are rigid and directional more than compensate for making good yield on those woven structures. But yes, this is a consideration that you have to keep in mind while doing this chemistry.
Thank you. Professor, I'm sorry, thank you. Professor Yaghi, I want to be fair to you because all the other Nobelists have been asked this very important question, and I feel you should answer it too. What is your favorite ice cream?
My favorite ice cream is pistachio.
Wow. Let's thank Professor Yaghi.